Okay, let's start. Yeah, so we have already seen many greedy approximation algorithms, and today we'll see one more. So we started with the vertex cover, moved on to set cover, traveling salesman problem, and then last class we saw bin packing, right? And then set cover also. Okay. So today we'll see another problem which is known as load balancing problem. Okay, so I briefly introduced to you this. So we are given a set of n jobs, J1, J2 up to Jn, and each job Ji, it has a processing time of say Ti. Okay, so J1 has processing time T1, J2 has processing time T2, so on. J. Okay, and we have m machines. Okay, so these jobs can be processed in parallel on these m machines, and they are numbered M1, M2 up to M. Okay. And we say that Ci is the completion time of job Ji. C1 is the completion time of J1, C2 is the completion time of J2, and so on. So what is our goal is to minimize the maximum completion time of any job. Right? So we want to find the maximum among all CIs, where Ci is the completion time of job Ji. So that much time we will at least have to spend running these machines. At least one machine will be running for this much time, right? And you want to minimize the maximum over all CIs, right? Because we want to save power, or let's say these machines consume uh, power or other things. So we want to minimize this maximum value. Okay, and this C max, it is also called the make span. Okay, just definition. And we assume that all jobs are ready at time 0. Okay. So plenty of practical applications to this problem. For instance, you could consider these jobs as some documents which you want to print, and these documents are of different lengths, so they have different processing times, and there are M printers. Okay. And you want to schedule these jobs on these M printers so that the maximum time for which one printer is running is as small as possible. Okay. So another way of looking at it is this partition problem. Let's say you have this Ti stored in some array, and you want to partition it into M subarrays such that the total sum of some subarray is as small as possible. Okay. So all these partitions, subset sum, or even knapsack, all of these are NP complete. So they are extremely hard problems. So this problem is also pretty hard. Using a very straightforward reduction, can show that it is NP hard. So as we have done in previous lectures, we want to find an efficient approximation algorithm. In fact, all approximation algorithms we have seen so far are greedy approximation algorithms. We apply some greedy strategy and show that the solution we have obtained in this way is uh, very close to the optimal, if not the optimal. Right? Okay, so let's see. So this is one sample example. We are given these 5 jobs, 5, 3, 7, 4, 6, and we have 3 machines. Okay, so let's say this job 1 takes 5 hours, job 2 takes 3 hours, job 3 takes 7 hours, 4 hours, 6 hours. So obviously you want to spend the minimum amount of time uh, allocating these jobs on these machines. Okay. So here's one allocation on machine one. First, you process the job which takes 7 hours. And so the standard assumption is that every machine at a time can process only one job. Only after that job is finished, then you can start the next thing, because a printer cannot print two documents simultaneously. Prints one document and then only it starts the other document, right? So here's one possible allocation on machine one. You give these two documents, one which takes 7 hours, that is J3, and then J2. All right. And then there is this another machine which processes J1 and J4. Okay. Then there is the third machine which just takes J5. Okay. So what is the make span here? Okay. Machine 1 runs for 10 hours, machine 2 runs for 9 hours, machine 3 runs for 6 hours. So what is the maximum number of time we are running a particular machine? 10 hours. Okay. So Cmax will be equal to 10 due to J2. And so this particular allocation takes 10 hours, but possibly there is some other allocation which takes fewer time, smaller time, right? And it is straightforward that if we took this job 3 hours, instead of scheduling it on M1, we scheduled it on M3. Okay. Then what happens is that M1 will run for 7 hours, M2 will run for 9 hours, M3 will run for 9 hours. Okay. So Cmax will be equal to 9 in this setting. Okay. Now, can we further reduce it to 8? Given all these things, can we get a maximum make span of 8 hours? Yeah, tell me. So we saw two different allocations, one which takes 10 hours, one which takes 9 hours. Can you get a possible? Can you reduce it further? Okay, we have an answer. So, yeah, so it's fairly straightforward to see that it is not going to be possible, because you sum up the total time taken by all these jobs, because we are only processing one job at a time. So it turns out to be 25. Right? 5 plus 3, 8, 15, 19, and 25. Right? And we have only three machines. Correct? So at least one of these machines has to run for 25 by 3 times. is standard application of pigeonhole principle, which you would have seen in some discrete math or whatever. Yeah. So at least one of these jobs has to run for 9 hours, because if all of these ran for 8 hours, we could at most cover jobs which take 24 hours. But the total time for which all these jobs are running, it is 25. Okay, so at least one of the jobs has to run for 9 hours. Right? So this particular allocation where machine 1 runs for 7 hours, machine 2 runs for 9 hours, and machine 3 runs for 9 hours. So 3 we have shifted from M1 to M3. Okay. Yeah. So now we want some uh, nice approximation algorithm which can at least give us close to the optimum, if not the optimum. Okay. So how should we do that? What's the algorithm for this problem? Right. So there are some stupid algorithms like you process all the jobs on M1 and M2 and M3 are remaining empty. Or you process all the jobs on M2 and M1 and M3 are remaining empty. So here we are not using the power that we have, is that we can run 3 machines in parallel. So that is why this problem is called a load balancing problem. It's because we want to balance our, yeah, we have only 3 machines. So somehow we want to balance the workload of each machine. Okay? So we don't want cases like one of the machines is too overloaded and the other machine is staying empty, doing nothing. Because that's the only way we can minimize the make span, right? When all the machines have workload equally distributed between them, then only the completion time of the last job will be as small as possible. Right? Yeah. So what do you propose? How do we balance the workload of all these machines? Yeah, is there a question? Someone has raised a hand. Okay. Yeah. So, okay. So let's see what we can do here. So the first job you can put it anywhere you want. It really doesn't matter where you put it. Okay. But the main decision we want to make here is that let's say we have allocated some jobs on some machines. Okay. How do we decide where does the next job go? Right? So that is the main decision. Which machine should it go to? M1, M2, or M3? Okay.
Uh,
Yeah. Is there a question?
Sir, for distributing the jobs, we can distribute it such that the time taken by each machine is equal.
Yeah. Time taken by each machine is equal. So how do you do that? That's the question. So in this case, it cannot be equal because the total sum is 25 and there are three things. So we can't take fractional time here, right? 8.33 is not possible. So yeah, you have to settle for something less, right? So one of them will take at least 9 hours. Okay. But this is a very hard problem in general, right? Because let's say you want to partition things, right, such that each subarray, uh, right, because we want to find subsets of, let's say, some 9, some 8, or, right. So subset sum is also a very hard problem in general. In fact, partitioning is also a very hard problem. So we can't hope to solve it exactly. So we want some kind of approximation algorithm. Okay, so we have some ideas, which is total jobs by total machines is 2. Okay, it's not exactly 2, but okay, let's think of it. There are 5 jobs and 3 machines. Okay, we will take pairs of job first. Okay, first sort the array and then go to the middle element and take the closest pair and iterate outwards. Okay. So let's say we have these jobs with 3, 4, 5, 6, 7. Then we take 4 comma 5 as the middle pair. Okay, you took 4 comma 5, then you took 3 comma 6, and then remaining 7. Okay. And this you are claiming is that it's very close to the optimal. That's an interesting idea. But we'll also need to prove that this is close to the optimal thing. Okay. Okay, there is one more thing, one more idea we have. Sort the jobs in descending order, the time. Okay. And Sort the jobs in descending order, and then what do you do? Assign first M jobs in M different machines. Okay. Then traverse through all machines and decide where to put the remaining jobs so that Cmax will be minimum. Yeah, so how do you make that decision? That's what I want to ask. Because you have to give an algorithm which runs in all possible cases. So you can't just say that we'll put the remaining jobs such that Cmax is minimum. We can take jobs one by one and put on that machine which has minimum number of jobs, which has minimum jobs. Yeah, that is a natural strategy which we can try. And then you also have to say something about the approximation factor, right? Remember, just giving an algorithm is not enough, which works nicely in one particular case, and you also have to compare it with the optimal solution, right? So, how close it is to be optimal, right? What is our approximation factor here? Is it twice, at most twice the optimal, or maybe 1.5 times the optimal? Right? That is the main argument we are interested in. Right? So whatever algorithm you are proposing, we have to compare it with the optimal solution. Okay. So what do we know about the optimal solution? Right? So one thing we know for sure is that if I sum up those running times and divide it by 3, that is at least the time one machine will run for. Correct? So we don't know yet what is the optimal. I mean, we know in this case that we have found this particular solution, but generally we may not know. Finding the optimal solution can turn out to be extremely hard. Right? Because finding the optimal partition here is not at all easy, right? Because we are given nothing. Like these are not even in sorted order or whatever. So whatever we have to do, we have to do it by ourselves. And then finding the partition so that the sum of each subset is uh, almost equal, that is another difficult problem in general. Because then you will have to consider all possible subsets and uh, check out their sums, and whichever one works, that will be our solution. Right? Okay. So here's one of the algorithms which one of you have already suggested is that we use this kind of greedy algorithms. Okay. Consider the jobs one by one and assign the current job to the machine whose load is smallest so far. So so one of you said we'll look at the machine which takes minimum number of jobs. Here I am just saying that the load is smallest so far because the number of jobs does not matter, right? Because it might be possible that the jobs are minimum, but they are taking long amount of time. Okay, so then you have to wait for a longer period of time before you can schedule a new job. Okay. So this is a more natural strategy is that we assign the current job to the machine whose load is smallest so far. So what do I mean the load? It is the finish time of the last job. Okay. So let's see another example, which is let's say I'm given this case 2, 2, 2, 3, 4, 6. Okay. Okay. So one of you saying optimal solution will be total time by total machines. If fractional take number greater than that is enough. No, no. So that is just a lower bound on the total make span. We don't know. So I mean, I could choose these values differently so that even if the sum is greater than 24 here, but 9 may not always be possible. Okay. So here I have chosen this 5 and 4 so that they sum up to 9 and 3 and 6 also sum up to 9. There is one 7 thing. Okay. But these numbers could be arbitrary. So you can't always assume that the optimum solution is total time divided by total machine. Okay. What we know is that it is at least the total time by total machines, but we can never be sure. Okay. So in fact, we need one more assumption here to claim that our solution is, let's say, at most twice the optimal solution of whatever. Okay. So let's say we take this example now. Here again, we have three machines and there are the six jobs. Okay. And we are given this processing times. Let's say this takes 2 hours, 3 hours, 4 hours, 6 hours, 2 hours. Okay. Now what's the total sum here? 9 plus 6, 15, 17 and 19. Right? Now if you divide 19 by 3, it is some 6.33. Right? So, but no matter what you do, you will never get a make span of 7 hours because these values are chosen in such a way that you cannot get an optimal solution of 7 hours. Okay. The only thing you could try is that you could put 3 and 4 in one thing and but then 6 has to be put somewhere. No, actually you do get here. You could put 2, 2, 2, 6 and 3 and 4. Okay. But in general, it is not the case that if you just uh, okay, there is one more question. Yeah, 6, 4, 2 and 2. Okay. Okay. So the thing is that when these values are very closely spaced to each other, you can always find such a thing. But let's assume that I pick very large values. One takes 2 hours, other takes 100 hours, another takes 1,000 hours. Then in general, it can be very difficult to get such kind of optimal partitions. Okay. So we need to give an algorithm which gives at least close to the optimal, if not the optimal. Okay. So yeah, you can check out if your algorithm gives the optimal for both these cases. Right? This was 3, 4, 5, 6, 7, and this case 2, 2, 2, 3, 4, 6. Okay. So here we'll see this algorithm, which is whenever we have to assign some new job, we will assign to the minimum load so far. Okay. Whichever machine has the smallest load, we will assign that job there. Okay. So what happens in this case? We started with this job J1. All the machines are initially empty, so you could assign this job to whichever thing you like, right? So let's say we assign it to M1. So this job 1 takes 2 hours. M2 and M3 are still empty. So the next job we will assign to either one of these. Let's say we assigned it to M2, right? M3 is still empty, so the next job we'll assign it to M3. Okay. And now what happens to J4? Right? So M1 is running for 2 hours, M2 is running for 3 hours, and M3 is running for 4 hours. So M1 has the smallest load, so we'll assign J4 to M1. Okay. So now this will run for 8 hours, this will run for 3 hours, this will run for 4 hours. So M2 has the smallest load, so we put J5. This should be J5 instead of J4. Right? So we'll put J5 to M2. Okay. And then the final thing. So now this will run for 5 hours, this will run for 8 hours, and this is only running for 4 hours. So M3 has the smallest load, and therefore we'll put J6 to M3. Okay. So this is one arrangement we get. So M1 is running for 8 hours, M2 is running for 5 hours, M3 is running for 6 hours. So the maximum time one particular thing is running is 8. Okay. And now we want to show that no matter what values you give me, this makes span will be very close to the optimal. Okay. In fact, I want to argue that uh, it will be at most twice the optimal solution. Okay. Yeah, and because the optimal solution can be much larger than just the average, right? Because if I take just 3 jobs, one is for 2 hours, other is for 100 hours, other is for 1,000 hours. Right? And if you add up all these things and divide it by 3, what will it be? Some 300 something, 366. But then you have to put uh, the 1,000 hour job somewhere, right? So it will take at least 1,000 hours. So one of the machines will be running for at least 1,000 hours. Okay, so the average is much smaller here, just 366 or something. And so we can't always say that we'll just take the sum of the processing times and divide it by the number of machines, and that will be the optimum. Okay. So we start with this algorithm and show that it is close to the optimum. Just the question is how close it is. So how do we compute the approximation factor here? That's the main question we want to address. Right? Whatever your algorithm is, how close is it to the optimum? Okay, and that is the more difficult part because there could be thousands of good algorithms, but can you compare it with the optimum? Okay, that requires some kind of combinatory thinking, and yeah, that's what we are going to see now. So the algorithm is correct because it is assigning jobs to all the machines, and the algorithm also takes polynomial time. That is also true, right? Because every time a new job comes, we just compare the loads of these machines and assign to that machine which has the smallest load. Right? Since there are only m many jobs, so all of these can be done in polynomial in m time. Okay? And the third part is approximation factor. That's what we will see now. Okay. So let JL be the last job that is scheduled on a machine whose load is maximum. So we have done all these schedulings on M1, M2, that's it. In general case, we have M machines. Okay. And let's say MK is the machine which has the highest load. Okay. So because that is going to decide what the make span is. The machine with the highest load and how much time it is taking. So I'm just looking at the last job here. Let's call that job JL. Okay. So remember that CL is the completion time and TL is the processing time total. So when was this last job starting? Uh, let's call it start time as SL. It will be the completion time minus the processing time. So at that particular time, it has already started. So what can you say about JL? Right. So why did we start on this particular machine? Because its load was the minimum compared to everything else, right? Otherwise, we could have scheduled it on some other machine whose load was smaller than this particular machine. Okay. So when JL is assigned, all the other machines, they are filled till the start position of JL. So at the start position of SL, right? So this machine at the smallest load, and that is why you assign JL here. Okay. So when JL is machine assigned, all the machines are filled till the start position of JL. Right. So all machines are filled means their total load so far was more than the start time of JL. Okay. That is why you have assigned it to this particular machine. Okay. So now what can we say about the total number of work which is done from time 0 to SL, right? So there are these M machines and we just want to decide how many hours of jobs have we completed from 0 to SL, right? So this machine has been working for SL hours, this machine has been working for SL hours, everything is working for SL hours. There could be some more time taken for these jobs. So it is at least M times SL, right? And you want, then we can conclude that this M times SL is at most the total number of hours needed to process all the jobs, right? Because each machine is working for at least SL hours. So the total number of hours required for all these jobs, that is at least M times SL. So yeah, good. So we have something about SL, uh, the starting time of this job. We have some bound. So SL is at most Tj, summation of Tj time divided by M. Okay. And then we also know what is the completion time. It is the start time plus the time needed to processing this particular job. Okay. So what's the completion time? And this is the quantity which we want to minimize, right? Because we said that JL is the job which is on the machine which has the highest load. Okay. So CL should be as small as possible. What is the bound we have here? It's summation Tj divided by a plus the time taken to process the Lth job. Okay. So this is one equation we have. And now we have to compare this quantity with the optimum make span. Okay. So what can we say about the optimum? So what is the relation between C star and summation Tj divided by N? That we have already seen that the optimum must at least be summation Tj divided by N, right? Because we could sum up the running times of all these jobs divided by M. At least one machine should run for that much time. Okay? So the optimal solution is at least this much. It may not be equal, it should be at least this much. Okay. So now this particular thing is smaller than the optimum thing. But now there is one more TL running, right? So that is the time taken to process the Lth job. And what can we say? How can we compare it with C star, optimum make span, right? So that is another calculation we want to make. What is the relation between C star and maximum of Tj? Okay. So C star should be at least maximum processing time of a particular job, right? Because whatever this job is with the maximum processing time, it should be allocated to some machine, and therefore C star would be at least this much, which is at least TL, right? So we don't know what's the processing time of this health job. It could be maximum, it could be minimum, but it will always be less than equal to the maximum processing time of any job, right? So now we have these two equations. C star is at least TL, and we also know that C star is at least Tj by M, summation for from J1 to N. Okay? And these are exactly the two quantities which we have, which is the completion time of L. Okay. And so from this equation, we get that CL is summation Tj by M plus TL. And we know that both these quantities are less than C star. Right? So C star should be at least summation Tj by M and C star should be at least TL. Okay. And so we get that this solution will be twice C star. Okay. So we get that CL is at most twice the optimum solution via this particular algorithmic approach. Okay. So it's a very straightforward calculation, which is that we want to minimize the completion time of the last job, right? So we found an expression for CL in terms of the input, and then we concluded that both these terms are less than equal to the optimum make span, and therefore our final solution will be at most twice the optimum solution. Okay. So any questions on this computation we have done? Okay. So if you are suggesting that some of your algorithms are better than this particular algorithm, the way to show it is that this factor should be less than 2. Right? Only then it is a better approximation algorithm. Right? So that will mean that you will have to exploit some other property that whatever your proposed solution is less than 2. Right? Maybe it's 1.5 times C star. So you have to exploit some other property of computing this optimum. Okay. But so far, all algorithms I know, they have this approximation factor too. Right? At least I am not aware of any 1.5 or 1.7 times. Yeah. So try to analyze the approximation factor of whatever your proposed algorithm is and try to see that if you get something better than. Okay, so if this is clear, I will start the next problem. Okay. Okay, so we get a factor 2 approximation algorithm for this setting. Okay, okay, so this algorithm is almost sorted. Everybody is clear with how it is running and how we have derived the approximation factor. Right. So our next problem is this, what is known as the weighted vertex cover problem. So we have already seen one algorithm, approximation algorithm, was a two approximation for the vertex cover problem where we just had to find the minimum size of the vertex cover. But now we are going to see a variant of this, which is weighted vertex cover problem. Okay, so we are not interested in just the minimum size of the vertex cover. Now each vertex we are giving some weight, WV. Okay. And we want to find the vertex cover such that the sum of the weights of these vertices is as small as possible. Okay. Now how do we find the minimum such weight? So if you remember what we started with vertex cover was that we'll pick a set of edges such that no two of them are adjacent to each other and we pick the maximal set and then we pick both the endpoints of those edges in our vertex cover. And that way we claimed that it was 2 approx. Now if there are weights on these vertices, what do you do? Right? So actually there are many practical applications of this weighted vertex cover problem. One of these is, let's say, you want to open some fast food joints, okay, or whatever shops. Okay, you want to open fast food joints, and uh, you have this map of the city, and so there is an edge between two vertices if there is a street connecting those two corners. Okay, and at every corner of the city, you want to open a fast food joint. So obviously different corners will have different costs, like depending on how buzzing that area is. And so that's what we call as W. So we want to minimize the total number of costs in operating these joints. But at the same time, we want to attract maximum number of customers to our joints, right? So ideally, we want that at every corner we have a fast food joint, but uh, so every street has two such corners. So even if we are able to establish at one corner some fast food joint, then we will get all the customers who are walking along that street to your joint, right? And there are many other applications. You could possibly think of something else, and all of them are special cases of this weighted vertex cover. Okay. Yeah. So any ideas how we are going to solve this weighted vertex cover problem? So we are given the weights on these vertices and we want to minimize the total weight of our vertex curve. Okay. Yeah, tell me any algorithm which is a good approximation algorithm. Okay, let's see some examples maybe. Right, so let's look at this particular graph. So let's see that there are just four vertices in this graph, and one of them is having weight 3, other is having 5, 3, and 4. Okay. So what vertices are you going to pick here so that the total weight of the vertex cover is as small as possible? Okay. Here we are giving weights to the vertices, which is opposed to the general case. Okay. Usually we have weights on the edges, but here we are giving weights to the vertices because finally we want to pick these vertices such that the total weight of the chosen vertices is as small as possible. Okay. So what's the smallest vertex cover weight here? Right? We can't pick 3 and 3 because then 4, 5 will remain uncovered. Okay. We can neither pick 3 and 4 because then this particular thing will remain uncovered. Similarly, we can't pick 3 and 4, this particular edge will remain uncovered. Okay. So I think the optimal one is 3 and 5. Right? So how do you find this particular vertices in our vertex curve? That is the question. So there are two things operating here. One is that we want to, in fact, we want to cover all the edges. So you can look at it as some kind of maximizing the number of covered edges. But at the same time, we want to minimize the total sum of these vertices. Okay, so there are two different things in operation here. One is minimizing something, the other is maximizing something. Okay, in fact, all of our chosen algorithms, approximation problems are like this. You are minimizing something and then you are maximizing. So one thing is we want to give an algorithm and then we want to compare it with the optimal. So one naive greedy strategy is that I pick the smallest weight vertices. Okay. So let's say I pick this particular vertex, but then you see that 4 comma 5 is uncovered, then you have to pick this particular vertex. Okay. But that won't give us a optimal solution. The optimal is just 3 and 5. No, that is also not optimal. Because then what happens is this particular edge will remain uncovered, or this particular edge will remain uncovered. You could pick 4 and 5, then all the edges will be covered, right? The so whatever greedy strategy gives us is that we pick the vertices with the minimum weight. So we picked 3, then we picked another 3, then we went to 4. And at this stage, we noticed that, okay, all the edges are covered, so we don't need to pick any vertex. Okay, so you will return a vertex cover of size 10 or weight 10. Okay, and then that you claim is the minimum weighted vertex cover, but then by being a little clever, you can choose these two things, 4 and 5. It is covering all the possible edges, and it is also a smaller weight vertex, right? So you want to give some nice algorithm and also show that it is close to the optimum. So what other strategy do you propose? What can we do to find the minimum weighted vertex cover? Okay, we are almost up with time, so you can maybe think about this problem. Can we do? Okay. Or if you have some idea now, you can share with me. Okay, so we'll see you on Thursday. Okay, then I'll stop this meeting now. We'll see you on Thursday. Oh, is there a question? Optimal assignment will be. Oh no, this was something else. Yeah, 4 and 5. Okay, then I'll stop this meeting now. Okay, there was one more idea that we can sort the array of jobs. Okay, then we can assign first n jobs to machines 1 to n. Then, okay, so let's say we assign first 3 jobs to machine 1 to 3. Then n plus 1 jobs to 2n jobs to machine n to 1 and so on till no jobs. Yeah. Yeah, but the point is that this will allocate equal number of jobs to each machine, but it won't tell us. Finally, we want to minimize the maximum time a machine is running, right? So that time has to come into the picture.
Yes, sir. Here the jobs are sorted according to the time taken to complete that job.
Okay, okay.
And so, if sir, if first n jobs are given to machines 1 to n, and then
Yeah, yeah. So I think, yeah.
and plus 1 to 2n jobs are given to machines from n to 1, and then we
Okay.
continue in that pattern, then roughly we will get
Yeah.
that each machine is getting jobs which takes uh so that
Uh,
such that the time taken by each machine to complete all the jobs is roughly the same.
yeah. Yeah. So it's the same idea which I had discussed later was that. So every time you are allocating a job to some machine whose load is the least, right?
No sir, no sir, I go according to the array.
Sorted, yeah, sorted thing, right?
Not array, yes.
Right. So for the first n jobs, so first you allocated first job to first machine, then second machine was free, so you allocated the second job there. Then third machine was free, then you allocated the third job there. Then finally you are checking that okay, all the machines have some or the other job, and now n plus one job will go to the, so first machine had the minimum load, so the n plus one job will go to machine one.
No, sir,
Right?
I'm not checking. I'm directly assigning according to the array only.
Sorted. Yeah, yeah, sure, sure. You are not doing it explicitly, but uh, roughly the idea is that, right?
Yes, sir, it implicitly is behaving that way.
Yeah, sure.
Sir, will this algorithm work?
Yeah, so it's the same algorithm, and approximate. So maybe you are saving some time by already sorting initially, but yeah, this algorithm works,
Okay, sir. Thank you, sir.
and it is a two approximation. Okay, we are over time now. Let's stop it here.